Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll start on Chapter 9 as a discussion of response models with factors and predictors. So we've considered simple models for designed experiments and observational studies where response variable is modeled as a linear combination of effects due to either factors or categorical variables, and predictors, what I'm calling continuous variables. Though strictly speaking, factors are also predictors. With design experiments, you get really sort of a pure Anova model where you get these clear set values for our predictors, probably set integers or something for our continuous variables. It's really clean and often some sort of balanced design. So for example, in an experiment comparing survival times of beetles, we had insecticide, which we had 4 levels of, and we had a dosage, either low, medium, and high, which had 3 levels. And both were indicated in the model as qualitative or categorical because we didn't have specific numbers going along with the dosage, for example. So a natural model to consider is a two-way Anova, which is what we did in that earlier chapter of dose and insecticide, and as well as having a dose by insecticide interaction to see whether differences in dosage, sort of the kill rate or the survival rate of the beetles, depended on which insecticide you were using. Okay, and we measured everything and so on and so on. All right, so that's sort of a description of that previous experiment. And in that model, we could fit a main effect model, or we could fit one with an interaction. Okay. Okay. So we're going to consider 2 different models. We're going to consider this additive model, which I call A, and an interactive model, which I'm calling I. Okay. So there is a connection between analysis of covariance models where we've got separate regression lines for each dose and two-way Anova models where the insecticide dose and the insecticide are treated as factors. That is, there's a relationship between whether you consider them continuously or as categorical. And so I want to show an example of that. So imagine we have our survival time by dose. So dose had low, medium, and high. So we have 3 levels, and we know from the previous chapter, or from chapter 8, the previous chapter on the quadratic models, that we can perfectly fit n observations with an n-1 degree polynomial. So if we have 3 levels of dose, and we have 3 parameters here, up to dose squared, then we can perfectly fit any 3 observations that way. So for example, here's some made-up data. And I've got, this is an additive model where A are all these red points. They're all stay low. Green are the high points. And basically the data, basically the low, so dosage at 10, 20, and 30 is low, medium, and high. And you basically start high, or the red dots are at about 4, and again at 4, and then drops down to about 1. So if we were connecting the dots, we'd have a horizontal line and then a downward sloping line. But a quadratic curve fits these data just fine. And here I've plotted the mean the curve with respect to the mean, but if you move this curve up or down, it's going to pass through the sets of points for any particular insecticide. Okay. I'll scroll down a little bit. I do expect you to read this section of the notes, even though I'm sort of zipping through here. Here is an example of those curves fitting through each insecticide by itself. For an interaction model, however, and I don't think I have show a plot of this. I do not. Right, so this is an additive model in that insecticide is a vertical offset of any of these lines, and these lines are parallel. Right, they're not straight lines, but they are parallel in that the distance between the lines, the vertical distance, stays constant regardless of dose. Well, if you had interaction, what would that mean? It would mean that for any 3 points for dosage could follow different patterns depending on which insecticide it was. So some could come down and then go down steeper, some could sort of stay about the same and then go down a little bit, whatever it is. And the point there is we can fit, if we had our two-way Anova model, we had all those interaction terms. If you go back to the chapter with the insecticide, beetle insecticide example, you'll see that we've got lots of interaction terms in that model. And I believe in that model we actually changed the response variable from survival time to the rate of death, and we end up with more of a parallel line structure, so an additive model. But the interaction model is very complicated. We basically need sets of betas to capture every set of means, and there's 12 means, so we're talking about 12 parameters to capture all those means. So whether you model it as two categorical variables, as we did previously, or take this path where we've got, say, a continuous variable in dose, which is this example, and a categorical for insecticide, you can imagine if we've got 3 dots for each insecticide that you get a different parabola fitting each curve. You could have some parabolas that are curved up, you could have some that are curved down, and so on. And so it's still going to be a fairly complicated model, but in this case we'll have parabolas instead of just all these additive terms in the two-way factor model. So here's a linear model. We've got insecticide dose, we've got the squared term for dose, we have the interaction, and we have an insect by dose squared interaction as well. And when we fit, I only give descriptions of this. Okay, I guess the point here is that here are the 12 regression coefficients, beta naught through beta 11, and we've got 4 insecticides, right? So we have a baseline case, and then we have sort of insecticide 1, insecticide 2, insecticide 3, maybe insecticide 4 is the baseline case. And these I's actually don't stand for insecticide, but are indicator variables for which insecticide is being offset from the baseline group. And we have main effect for dose, and then we have all these dose squared. We have a dose squared term, and then we have the interaction for the different slope terms with dose, and then we have an interaction with all the dose squared terms. And so that allows us to get different parabolas for each insecticide. In particular, the baseline group is beta naught plus beta 4 dose plus beta 5 dose squared. That's the intercept, the linear term, and the quadratic term. Let's look at for, insecticide B, say maybe this I1. Okay, this indicator variable for the second insecticide. So that means if you add these two numbers together, you'll get the intercept. Then we've got dose plus, so beta 4 dose and beta 6 I1 dose. If you add beta 4 and beta 6, that is the slope term for dose for that second insecticide. And then we have beta 5 dose squared plus beta 9 I1 dose squared. So beta 5 plus beta 9 is a quadratic term for that second insecticide. And you can go through that for I2 and I3 as well and get different regression equations for each. So you've got a different parabola for each insecticide. All right, so I recognize that me trying to describe this quickly in this video format might be confusing, and of course that's never my intention, but there is a relationship between being able to model these things using, say, analysis of variance, where we had a two-factor, two-way Anova in a previous chapter, or whether you want to treat these variables as continuous and use regression modeling. In fact, you will get the same model predictions with both models for the observed levels of your design. But it is the spaces in between that you could miss. And that example was basically shown back in chapter 8 when we had, so we were fitting every point just fine, but it's the spaces in between that we're missing or, making unreasonable predictions for. Okay. Be careful. I also have a second point here, is that there's quite a bit of complexity here that probably seems confusing because I'm glossing over it a little bit. And it may be intimidating, but the point is that there's a lot of study that graduate students in statistics go through. We have a core set of important courses in experimental design, regression analysis, linear model theory that are all above the level that we're learning it in advanced data analysis 1 and 2. And that there's a lot of subtleties in the modeling that a good data analyst will be keenly aware of. Okay. Be careful. These tools are dangerous. In particular, I emphasize checking model assumptions right away, because one of the most dangerous things a data analyst can do is to fit a model, look at the R-squared, and consider the day done, because that's not where regression modeling happens. It happens all in the diagnostics, checking to see whether the model you're fitting even makes sense at all. And you're all getting great practice at that. All right, I want to make some comments on model building. Just some general, sort of take a step back, bigger picture comments. So a primary goal in many statistical analyses is to build a model or models to understand the variation in a response. And fortunately, or unfortunately, there's no consensus on how this should be done. What you learn from me might be different from what you learned from other professors. And the strategies basically shouldn't conflict too strongly, I think, in the primary principles, but there's some subtlety and some choices that can be made in terms of what you want to prioritize. So ideally, theory would suggest models to compare, but in many studies the goal is to provide an initial model that will later be refined and validated or refuted by further experimentation. For example, you might collect a set of data and as to sort of help you generate some hypotheses. So maybe you've got a lot of predictor variables, maybe 10 or 20 predictor variables, and you collect 50 observations because it only costs you several $100s to do that, and then you fit this model and you realize that of these 20 predictors, only 4 or 5 seem to be important in modeling the response. Beautiful. Now you've got sort of a more focused you've learned something, and you can then take by further experimentation, collect more data, either as an experiment or an observational study, and see whether the model that you fit initially is validated. Or maybe you learn a little bit more and you refine your model. Or maybe, in fact, there was something unusual in your first data collection or your second data collection, and the two models, you've got generate two models from the two separate data sets that actually conflict with each other. So that is one way of going about doing data analysis, and the sorts, depending on the sorts of goals that you have in your study. Okay. One extreme view in doing modeling is that the selected model should only include effects that are statistically important, meaning, say, all your coefficients are significant at an arbitrary alpha type 1 error level, say 0.05. Okay, so as we've sort of been doing in class, you start with the full complex model, do backward selection until all of your model coefficients are significant. Okay, so that's one strategy. Another strategy would say that, well, regardless of whether they're statistically important, we should include certain variables because they are scientifically important, whatever the scientifically part means. One situation of scientifically important is in epidemiology. So often data are collected on people to model health outcomes, and we always collect a person's age, age, gender, race, socioeconomic status. Okay, maybe there's a few others that are really common, but let's say those four. Okay, and then you also collect lots of other variables like smoking status, how much exercise you get, whether you're taking certain drugs, all sorts of things that might impact whatever response variable is. Say, your survival time after being diagnosed with a certain disease. So age, sex, now I'm trying to remember race, and socioeconomic status. Those four, as an example, they basically influence everything. Age, in particular, influences everything related to health. Okay, sex will, because of different hormones and other sort of lifestyle issues. Socioeconomics makes a huge difference because people who are wealthy live, easier, more comfortable lives. The strains that they put on their body are often by choice rather than instead of, people who are lower socioeconomic status, say who are working in construction or the sort of the harder physical labors, they're at much more risk for injury, and they put much more strain on their bodies without having as much time for rest and recovery. So in those sorts of studies, an epidemiologist would always include age, sex, and these other variables, because while there may not be a statistically significant difference between, say, the race of people or their socioeconomic status, we know that life experience is often largely influenced by those variables. And so they'll include them in the model regardless of whether they're important. So then your interpretation of the other coefficients, for example, whether smoking is important, that's important after adjusting for age and sex and race and socioeconomic status. So what's the influence of smoking above and beyond these other variables that we, from thousands and thousands of studies, we know are often influential on a response health variable? Okay. Don't worry, I won't talk that long for every paragraph. Okay, so those are the two extreme views. A difficulty with implementing either approach is that importance is relative to the specific goals. Okay, so why are you building the model, and what do you plan to use the model for? Are you modeling it to sort of understand the relationship as a prescription, or are you developing the model to make predictions of new observations? Are you developing a model to understand how a certain effect or set of effects influence the response? What is your goal? And in JASA, which is probably the primary journal in statistics, the American Statistical Association is our national organization, and this is the primary journal for that. There's a comment from over 20 years ago: science is an iterative process in which competing models of reality are compared on the basis of how well they predict what is observed. Okay, so if a model predicts well, that model will be preferred over a model that doesn't predict well. Okay, that's what the rest of that quote says. They argue that models should be selected using Occam's razor. Okay, so this is how you learn things on the internet. Type it in and you click on the first link, which is Wikipedia. Oh, that left. Okay, so Occam's razor, or law of parsimony, is a problem-solving principle which says among competing hypotheses, the one with the fewest assumptions should be selected. Or basically, if you have a set of models, the simplest should be preferred. That's the basic idea there. And so that's one of the primary principles that many use for doing model selection. A widely accepted norm of scientific. Okay, great. So their ideas are fairly consistent with the first extreme, to only keep variables that are significant, but can be implemented in a variety of ways depending on how you measure prediction accuracy. So we've got, in our class, we focus on frequentist approaches, but there are also another school of statistics called Bayesians, which is a learning model where you've got some prior knowledge, you collect data, and when you combine what you knew previously with what you observed in the data, when you combine those, you get a posterior. That's basically updated knowledge conditional on the data and on your priors. Okay, that's what the rest of that sentence says. Sometimes I look away from my notes as I talk, and then I come back and see that I've typed it out. And there's other, there's plenty of model selection criterions. Okay. So this is basically the strategy that we've been using in our class. A simple compromise between the two extremes might be to start with a model building process with the most complex model that is scientifically reasonable. So we start by fitting a full model, and then systematically eliminate effects using backward elimination until we arrive at a model where all remaining predictors are significant. And whatever that maximal, most complex model is, we want it to be complex enough to capture all the interesting features of the data, but not so complex that it's basically impossible to interpret. So we often start with a maximal model that has main effects, interactions, and maybe two-factor interactions, and maybe some quadratic terms. And that's often plenty. Okay. All right. So I'm going to skip a little bit, but I do want you to read some of these things. We have discussed the hierarchy principle previously. I'll make maybe the one point here that, say you have a certain model, and we have three effects, A, B, and C. And say in our model we have effect A, B, C, and the A-B interaction. So if we're going to use backward selection, the only candidates that could be dropped are C and the A-B interaction. And that's because we can't drop A because we have it the A-B interaction is relying on A to be in the model. Same thing with B. So that hierarchy that we drop the highest order effects first limits which terms can be dropped at any particular step. Okay, so that is what I wanted to say for the introduction of this chapter. In the next video, we'll be looking at this fairly complicated example to look at the effect of sex and rank, that's professor rank of assistant, associate, or full professor rank, on the faculty salaries from a small college from the 1970s. And the purpose of looking at this example, if I jump down to the very bottom, I'm not really giving any spoilers away, I don't think, is that there was an issue about, this was actually from a case in law, about whether women were being treated unfairly or not. So, maybe I won't, boy, this is a long example, but a lot of it is quick to explain because we're doing model selection and so on. So,